Welcome to SAS Advanced Week 1 review video. So we learned a lot during the first phase of the advanced level or the first week of the SAS advanced level. And we were continuing building upon the knowledge we had on the data visualization using SAS output delivery system graphics, whereby we continued with the information conveyed in the foundational level, whereby we completed that phase of the training with the single cell graphs using the SGPLOT procedure. And now we began the advanced level with the multi-cell graphs using SGPANEL and SGSCATTER. So to just contrast that the SGPLOT procedure, we saw that it was producing single cell plots. And if you would want to just obtain multiple plots for the same particular customer groups, just to convey separate plots for each customer group in one cell. So we have multiple graphs, which are the cells conveyed on one visual, and that is what we were calling multi-cell graphs. And we saw the power of creating multi-cell graphs using the SGPANEL procedure step, and it just allows us to understand our data on even a deeper level, like each category, or understanding the distribution of the cells among each customer group. Okay, so here we can understand the distribution perfectly, and we have split the panel into two separate panels with each row sharing its own x-axis, so that you can appreciate the sales across countries for different customer groups, and you can see how each sales group or customer group is performing on their sales, to even focus more attention on them if need be. So after looking for multi-cell, or rather creating multi-cell graphs with SGPANEL, we also learned how to create them using the SGSCATTER procedure, which was allowing us to create multiple graphs or multiple scatter plots just in the same particular grid. So you can see you can either use a compare statement, so that you can list or rather get separate plots for your particular comparison, or you can use the matrix statement for the SGSCATTER procedure, so that you can just receive all plots in one go, whereby every variable is used to assess the relationship between each other, as is evident using this plot here. Finally, we learned how to combine all these graphs into one display, as we have done with those procedures. So for the second lesson of the advanced level week 1, we created some graphs with the SGPIE procedure and the SGMAP procedure. So we experienced the pie charts and the donut charts. That is after going through the previous day's assignment. We created pie charts and viewed how to just modify various attributes in the pie chart, like the pie slice colors and the attributes that they represent, like the data labels on the particular pie chart or the final visual, and the data label display and the data label attributes, their size and weights, and the size of the ring for the donut chart, as you can see here, as well as for the pie chart, which was just requiring us to use two statements, the pie statement and the donut statement, all under the roof of the SGPIE procedure step to come up with those visualizations. So to just demonstrate the donut chart, and adding all these statements or options after the forward slash in your particular plot statement, it allows you to customize or enhance your final visual so that it meets your audience's needs and you convey the best information possible that will be useful to guide your audience or your team, whomever you're presenting your data to. So we also use the SGMAP procedure that helps us to overlay maps over our data so that we can understand, and the data should be georeferenced for that matter, so that you better understand how your data set is being affected or its distribution in your real world areas. Perhaps you have branches in different locations and you might want to understand these relationships in the real locations, and to do that we create graphs using the SGMAP procedure. And some statements facilitate, like the OpenStreetMap statement in this scenario allows us to overlay a scatter plot onto the map to better understand our visualizations or the relationship between those particular variables across the countries. So this is more informative in your business decisions because you can literally see exactly how the relationship occurs. So we learned that if you do not have a data set that contains these georeferences, we can add our own through the geocode procedure, which utilizes datasets from the Maps GFK library that SAS produces and Maps SAS libraries, and they contain every city in the world and continent in the world and just their location or geo information. So by geocoding or using the geocode procedure step, we can assign this geo information to our data, and we can use our newly created data, or rather not newly created, but we can specify the columns that contain this information that can be used to search across these particular data sets and provide that geolocation or the coordinates in real time or the real coordinates. And the method option just chooses which geolocation method to use to apply the coordinates to your dataset. So if your dataset has a zip column, it's better off to use that. And the state column, city column, and the address column can be used as well. So various types of plots can be applied as well, like the bubble plot in this example. So we can overlay plots on top of maps to just understand, for example, which points convey interesting information and we can act upon them. For example, in this bubble plot, the size of the bubbles were curated by the capital that the population gains in each of these countries. And we can see that some countries have a bigger capital than others, which is very informative in business scenarios. So that is what we covered in the SGPIE and SGMAP in lesson 2, and this concept particularly is overlaying plots and annotations on the maps, as you can see, by specifying these annotation options and further customizing the marker attributes. We annotate and overlay these annotations on the maps that are produced using the SGMAP procedure step. So after we were comfortable with that, we proceeded to lesson 3, whereby we have covered enhancing visualizations with the output delivery system. And we realized that we customize or enhance visualizations using statistical graphic annotation datasets, which can be created using assignment statements. They can be created using the data lines and input statements, and they can be created using the SG graphics annotation macros, all which their purpose is to create an annotation dataset that contains annotations such as lines, texts, and shapes, and their attributes, so that they can later be applied or overlaid to a plot to further annotate it and convey useful information. Just in effect, I would like us to create this particular macro annotations, that is a rectangle and a text annotation, and apply them to the scatter plot, assessing the monthly sales in USA for the year 2020. So first you create your annotation dataset and you specify it using the SGANO option in your plot or SGPlot procedure statement step. So that SGANO specifies the annotation dataset which is applied to your final plot. So we added an annotation and a rectangle, a text and a rectangle annotation, which can be seen here, and their values indeed have been added. And the x1 and y1 represents the positions. So if you edit the positions, they are going to move about. That is the x1 and y1 variables, and the height and width affect exactly that. That is the height and width of the rectangle annotation in particular. So we also had attribute maps, whereby you can just edit specific observations in your dataset and assign a special ID to them, so that only those observations will bear the particular attribute specifications that you give them. So that is what we were calling the attribute map dataset. Remember that it maps these attributes to the observations that you will have stated in your attribute map dataset. So we created one using the input and data line statement for the countries France, Germany, and Italy, and assigned them the universal ID country attribute, so that all the particular countries that meet this statement or meet this ID, they are going to have this attribute mapped onto them. That is, going along with these columns, they are going to have a fill color of dark gray and line color of dark gray. That is for France. And the markers that will represent Germany should have a fill color for light steel blue, and for Italy slate gray. And we apply the particular data that contain, or the attribute map data, we apply it using a different option from the annotation dataset. So we don't use SGANO, but we use the data attribute map dataset to specify the particular data attribute map dataset. So after creating the attribute map, so that you can map these attributes to your desired observations, you can apply it to your plot, and you're going to see that the markers for the plot are going to appear specifically as you specified them. So using attribute map dataset and SGPlot datasets allow you to enhance visualizations with ODS graphics. in conclusion, we went to lesson 4 today, and we have just concluded with the data manipulation techniques. So before that explored all the ways of creating the output delivery system graphs using the procedures, and before exiting the whole visualization topic, we have explored how to use the graphic template language as well. So the graphic template language only contains functions that regular procedures might not contain. For example, there might be a plot option that you may not have, or a plot type for that matter, that is not available with an SGPlot. And in contrast to that, you have the same plot type available with the graphic template language. So when we use or when we draw graphs in SAS using these procedures, it utilizes predefined graphic template language statements to suit the particular plot we have requested from a procedure. So in contrast, the graphic template language is like the syntax of the plots obtained from certain procedures. So to demonstrate, we created a histogram whereby the SGPlot procedure creates only vertical histograms. There is no way to orient your histogram to a different shape, but in contrast, or rather orientation, in contrast we have the graphic template language, which allows us to first of all define your particular template using the define statistics graph, and we were just giving an intuitive name to show that we are requesting a horizontal histogram, that is histo horizontal, and the begin graph statement coupled with other statements allow you to define your particular visual how you want it using the graphic template language. So the graphic template language contains two blocks. You need to create a template using the template procedure step, and then you need to render the template using the SGRender procedure, and that applies the specifics that you've specified in the template to the dataset. So you can see that in the orient option here, the histogram option has more robust statements options in the GTL context than in the output delivery system procedure example using SGPlot here. So by creating that template and applying it to the particular data set using the render. So this is just one of the reasons that you might want to use the graphic template language despite its lengthy format, just to access perhaps plots and features that are not otherwise available with the regular plots. So finally, we appreciated the data step because we have already been encountering the data step all through the foundational and advanced level lessons. But now we understood the program data vector and how the data step performs its executions under the hood to come up with the final output table. So we discovered that there is a program data vector that defines how records are read into the particular data step, and we just grouped that into two phases that the data step occurs to carry out its function. So it goes through a compilation phase that is creating the program data vector in this example. That is because the set statement is the first. The program data vector is created by copying all those particular columns and properties of those columns from the parent dataset. After copying these attributes, it will begin to read in the first row and check for the particular assignments of new variables, check for the constraints whereby the data is being subsetted, and select observations that meet all your constraints even before dropping the particular variable. So we saw that the drop statement, the variable that you are dropping or keeping, will be dropped after all the rows have been input into the last or final table. And to just view these executions in action, we have explored the put log statement, which allows you to view the program data vector in each step at the log window. So in this example, we wanted to see the first two operations of the particular program data vector in choosing the specific rows. And we can see using the put log statement, we have identified the first two rows that were assigned into the storm complete dataset using that in the execution phase. So there is the compilation phase, which creates the PDV, and the execution phase uses that PDV to select the particular observations that are meeting all these constraints, after which, if there was a variable to be dropped, all while it has a drop flag onto it, it will be dropped after all the desired variables have been put. Next, we wanted to learn how to create a cumulative column using the retain statement, so that after the first row has been created in the output dataset, we know the execution phase is like an automatic loop, and the data step goes back up to the set statement and reads the second row. So in effect, we will not be able to create a cumulative column. And in this example, we were counting we wanted to see the total number of rain daily for every day of 2017. In effect, if we wanted to see the total rainfall of day 1, that is the total rainfall in day 2, we require an accumulated column. So that is the rainfall for day 1 plus 2. If you want total rainfall for day 5, the addition of rainfall from the preceding days. So to do that, because of the behavior of the PDV to just discard everything upon reading the same, or rather the second record, we use the retain statement, so that as the program data vector is reading new records in, the records for the particular column you specify after each iteration is retained to be manipulated in the next program data vector function. So we have also appreciated the SAS functions to manipulate our data. In this case, the scenario was to give 5 quizzes to students, drop the lowest 2, use the highest 3 to just get the average. So the called routine sort n just sorts the rows in order from in ascending order, and the columns which have a lower lower values are pushed to one side, and higher values to the other side. So in effect, we can see that the 5 quizzes have been arranged in order from the lowest to highest, and that is row-wise. So we can see it is in ascending order row-wise, and that will give us the 3 highest quizzes, which will be from quiz 3 to quiz 5, as we can see here in the code. And to get the average of the quiz from the mean of the highest 3 quizzes. So we have also just gone through some functions to help us to create this particular variables. So we have the largest function here, which picks the largest of a particular column that you specify. And we also have the mean function here, which just finds the average value of the 3 columns there. So to just assign perhaps student IDs, we can specify it before the set statement to avoid the program data vector manipulating it together with the rest of the variables. Remember, if you put it after the set statement, the program data vector is going to read the values from the already specified data set, which we will not have that particular variable. So just on top there, by specifying the student ID and using the random function, so we want random integers that are 4 digits to act as the IDs, so from 1000 to 999. And those are how you can use numeric functions to manipulate data. Here we have used the random function to create a new column, that is a manipulation, and we have used the largest function as well in our example to just produce desirable columns. So in that we have concluded the advanced level of SAS statistical software.